So in fact, there is only one sequence here that matters, and it has to be a fixed point. Right? One way of thinking is you have an infinite number of equations like this. Right? Per se, you can write them like this. I mean, you know, this is this. Okay? That's a mapping from an infinite sequence, right, into these three, and there is an infinite number of these variables, so in fact this is a mapping from an infinite sequence into an infinite sequence. And then equilibrium is a fixed point of that mapping. Right? So one thing you can try to do is to study that mapping directly and try to see if there is a fixed point theorem you can use. I think some people actually tried that. Now I don't remember anymore. This is a 30-year-old literature. Some of the technical details I have forgotten. I think there are a couple of proofs under special conditions that use Tarski fixed point. That depends on monotonicity of the mapping. The mapping is monotone, and so you show that there is at least one fixed point. The way Romer tries to go, and the way then stops halfway, and then we go with Aldo, is, in my opinion, simply more general. We just try to show that once I set this equal to that and I look for a fixed point, I have to solve a perturbed Euler equation. And so we solve the dynamical system. Dynamical system has a given initial condition, K0, that's given. And it's equal for everybody, you're identical to me, so the initial capital is identical. No problem about that. And I go look if there exists at least one path. In fact, the question is how many paths exist that satisfy this perturbed Euler equation. I'll show you in a moment why it's not exactly an Euler equation. Okay? And we show that it's true, and in fact we show that it has a unique solution. So even if it is not exactly the Euler equation of a concave programming problem, it has the same properties from the mathematical point of view, and you get to the same conclusion. Okay? That's the way we go. But that's mathematical, that's the problem. Okay? The problem is, I think Paul discusses this, right? You have to map a fixed point from this into this for all t's, right? And if that thing has a value of this, for which gives back the same value, then that's an equilibrium. Okay? When you do this here, you can simplify your equation, right, by calling f of kt g of kt. I think that in the paper we actually do the opposite, because both of us like to work with f. So the paper starts with g and then uses f as the final one, because it's the one that we use more often. But I forgot today, so see, I remember my habits. And so let's call it g, okay? So what is the equation looks like? It's u prime evaluated at g of kt minus kt plus 1 equal delta u prime evaluated at g of kt plus 1 minus kt plus 2 multiplied f1 evaluated at kt plus 1, I'm sorry, g, oof, no, sorry, in fact I call f1 of kt pi of kt in the paper because of this. Okay? That's the private return on capital. Now what's the problem of this? The problem of this is that it needs not to satisfy the second order condition on the arguments that the Euler equation satisfies. Right? So in particular, in the Euler equation, this is monotone decreasing, but this doesn't need to be monotone decreasing. We go through this. Right? Why? Because, for example, why the margin of productivity of your own capital is decreasing by assumption in your own capital, it may be increasing in aggregate capital, and therefore the total derivative may become positive. So instead of having pi decreasing in k, pi may actually be increasing in k, if the externality is strong. All right? The same is true here, right? G in the standard model is just a concave function. But G in this model may be anything, right? Because we have introduced this externality. The externality has no rules other than being positive. So per se, the production function can be partly concave, partly convex, but it can go up and down. There's no rule, right? In fact, if you use, people often in those years use this as an example. Okay, that's the external. That's a terrible example because the aggregate production function is like this, right? Marginal productivity keeps increasing there. In fact, people got also pretty stupid results out of stupid examples. Okay, so you cannot just take that and play with that like you do with the standard model. It just doesn't come out. Okay? Which is why we go through the mess we go through. All right? But I don't want to hold you. I mean, if you're interested, I'm happy we can actually meet separately or have a session and go through the steps of the proof. But I don't know if it is worth it. Okay? What we do, but let me tell you the way then the result is organized. When you look at this and you say, okay, given the assumption I've made, there is extremely little discipline on this thing. This thing can be a mess, okay? Then you actually realize that even if you have added an externality, it's not obvious that there is a bounded growth. Because the externality may be not strong enough, and the initial production function, the one on your own capital, may be lots of decreasing return. So actually you could have equilibria with externalities that are bounded per se. Right? So first point, you want to study the bounded case. Another case in which you could have boundedness is because the externality is not positive, it's negative. But I tend to think, and I want to have the discussion second part of the lecture today, most externalities out there are negative. And in these cases, there are very notorious and big externalities we notice everywhere. Congestion. Right? Your plant takes away land from mine. You pollute mine. You obstruct my thing. Forget about the so-called pecuniary externality. Your demand for labor increases the price of my demand for labor. Okay? People sometimes even make this. Well, you know, those are not externalities from the point of view of competitive analysis. Those are not external effects, right? But there are people that confuse that. They think that, oh, your demand is a negative externality of mine because you increase the price. Yeah, sure. But there could be physical externality, that's what I'm saying, okay? And so we studied that. So the first case we studied, if you look at the paper, we studied the bounded case. Okay? So the case in which it is bounded, what's interesting? Well, we showed that in fact, because of the fact that this is no monotone decreasing, there could be more than one steady state. Very simple. I mean, nothing special, right? This one would go up and down, and so, right?
And the convergence stories.
And then they become alternative. So the kind of paramount example is this, right? Because at steady state, when the thing is bounded, this disappears. So all the mess that this can create goes away because it's consumption and consumption. So there's only this. But this, could be doing like this. Right? And so you could have three steady states. Okay? The first and the last are attractive. That's the lucky steady state, the unlucky steady state, depending on the initial condition, and the middle one is unstable, right? It's an example often used. I have no idea how. We get so captivated by this example, so simple, that we think that they're rules of the universe. I don't know much this is the rule of the universe, right? That there is, if you start poor, you remain poor. If you start rich, you become rich, and the middle ground never exists. Whatever, maybe. I don't know if that's the effort. There is one example that works to me, and in fact it's in the case of congestion externality, which is violation of traffic laws. Right? But it's no longer poor and rich. It's very little amount of violation, or almost zero, a lot of violation. And that's obviously a world in which the middle equilibrium, which I violate the rules only once in a while, is unstable. Because if you start violating, my best response is violating, and then he violates too, and then hell, we all violate, right? Anybody that's been in Naples versus Stockholm knows what I mean, right? But other than that, honestly, cheating is the type of equilibrium that leads you to extreme position. Either you almost never cheat, you cheat by chance or as an error, or because particular individual cheats, but it's a rarity and gets severely punished, or everybody cheats. Italians are expert about this, so we don't need to, we have just a prime minister that has managed to cheat on all his CV, and everybody says, everybody does it. I mean, what's the big deal? And that's beautiful. He's going to get along well with Trump. Okay, so that's the first case we study. The second case we study is the same, but unbounded. This, if you want, is the Romer case, okay? Okay? That's the case that Romer studies. This is not, I think this was studied, well, maybe it was studied by nobody before. I don't remember, okay? Nishimura and Decker, as I mentioned, studied the case in which the production function was not concave, but they're not studying externalities. So ours is kind of a generalization, if you want, for the bounded case of what they do, but nothing special. This is the case that Paul wanted to study, and we characterize it completely. There, the result is the complicated one, but the intuition is, well, you know what, the intuition that we had was, look, this thing has to start from a, so what is that we had to solve? What we had to solve is actually the fact that we could not do, let me give you the mathematical intuition about it that we said. As I said, this is a perturbed Euler equation, okay? What's the property of the standard Euler equation, the one we saw last week? That it's tantamount to a dynamic programming problem, right? And the dynamic programming problem, right, because there is a policy function. And the dynamic programming problem is great because we can study the dynamics. Capital stock today, capital stock tomorrow. Bang, 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 right? Here, no way. Given K0, K1, K2. Continuum equilibrium. And so on. Right? Transversal condition didn't pin down shit. Why? Because there is no saddle point. Right? It's the unbounded case. There's no steady state where we're going. Right? So there was no way of regulating it. Yes, we could go the way and just stop and say, well, let's bound this above and below. And that's all. Just by using boundaries. But we said, well, there's got to be a way of finding it. If there is more than one path inside there is an equilibrium. So we said, if we go the sequence way, we are stuck into the thing. On the other hand, one way of thinking at this stuff is that it's one of these examples which a change of variable in mathematics can help. I'm not such a good mathematician, but this is something I learned from Luigi. Sometimes changing variable help. It changes in integration, at the elementary level, it changes also. You can start thinking a thing in a different point of view, and then you bring it back. And so we said, well, it's true, I have x0, and I have to choose x1 and x2. But one way of thinking is, given x0, if I choose x1, I've chosen a growth rate. Then, given that, the dynamics is a mapping in growth rates. Right? from lambda, I call it lambda t, to lambda e to t plus 1. That's a mapping of a real variable into another, and to the extent we're willing to assume, which is the key assumption, right, that the growth rate cannot become infinity. That's all we assume, if you notice. That it has an upper bound that I think we call L, capital L. Then that's a mapping from an interval into an interval. Right? True, it's parametric on the choice. So what we actually have is a family of mapping. Right? And this damn family moves because as the map maps lambda t into lambda t plus 1, then it also changes its state. It goes from xt to xt plus 1. So it's a different mapping. Right? That was the idea. The idea was, let's take this equation and write these variables, taking xt as given. So this becomes g of x minus x times lambda 1, right? And this becomes x times lambda 1, and this becomes x times lambda 1, lambda 2, and this becomes x times lambda 1, right? And then obviously for every t, you call it t, right? Parametric on x, this may give me a mapping from lambda t into lambda t plus 1, okay, that is conditional on x. And I do know something about x. I know it grows. Like by assumption, it's growing. So this mapping is being driven by an x that keeps growing. And I'm not interested in what the mapping does at low level of x because I'm only studying the asymptotic behavior. So I'm interested in what the mapping does when x becomes big. Okay? So that's the old trick. Okay? The intuitive part of the trick is that. The rest is just math. Okay? Which is because x becomes big, the production function becomes almost linear, and so you can start playing with that. All right, that's what drove us. Okay, and given that, you just check the second order condition. You see, that's the cool thing. You look at that and you see that it's an implicit function, right? If you just put minus here and set everything equal to 0, right? And you say it's an implicit function. Given x is an implicit function of lambda 1, lambda 2, and I want to extract lambda 2. What is the implicit function theorem tells me? That if, I have a well-defined function, if the specific derivative doesn't vanish on the domain, right? You remember? G of x, y as a function y equal f of x if dg and dy is different from 0 over the whole domain. Wow, lambda 2 is only here. And the only way it comes out is through the second derivative of the agility function. All I need is strict concavity. It's exactly the same assumption in the standard model. Right? That's the cute thing. So I do have this function. It's well defined, it's not a mess, it's just, I can study it. Okay, so that's what we do. All right, so that's what we do, and we show what we talked the other day. We show that the equilibrium exists, and it is this funny equilibrium that actually lambda t is larger than lambda t plus 1, and they converge to lambda star. All right? So it looks like the model without externality. The economy grows, it grows forever, the growth rate are decreasing, and it converges to balanced growth. Moral, externalities are good for nothing. They just make your life miserable. But they got me, an extra paper, so I didn't mind. Actually got me 3 or 4 extra papers, so I didn't mind. Then I got bored. I said, enough. I get easily bored. All right. So that's for the one thing. At that point, given that we were having fun, we said nobody's ever going to consider this, but both Aldo and I are fan, or maybe are negative fan of the one sector model. We think it's very special, silly model with a lot of crazy properties. it's very easy to use, but it has a lot of crazy properties. And so we said, what will happen in two sectors? And so we play with two sectors. So the second part of the paper is just the same exercise, two sectors. And again, in two sectors, you can have bounded equilibrium and non-bounded equilibrium. And there we show that you can get anything you want. It's a mess. But if you're really curious into how stupid and crazy results mathematical economists can prove by making very strong assumption, if you look at the paper at the end, we work out an example of a two-sector with an input-output Cobb-Douglas technology and an externality, and we show that it has a strange equilibrium with a strange... there is a follow-up of that. I have a paper with two Japanese co-authors, Kazuo Nishimura and Makoto Yano, in JET a few years later, where we take that same model and work it out completely. Yeah, but it's not a serious paper. We show that the set of equilibria of that growth model has the structure of a Cantor set.